So welcome to lecture 8. So in today's lecture, we'll be discussing interacting quantum field theories. So let's start with some introductory comments. So far, we have only seen free realistic field theories. Now, this should be obvious from the fact that the equations of motion, that is the Heisenberg equations of motion, are linear. For example, we saw that for the real Klein-Gordon field, the equation of motion was given by this equation. So this is a linear equation, and therefore the different modes in the Fourier expansion of phi of x. So we saw a Fourier expansion So the different modes, that is the different values of the 3-vector k, will not interact because of the linearity of our theory. We can also see this in another way. We saw that the Fock space states are all eigenstates of the Hamiltonian. So we had Fock space states which had, say, particles of different momenta. And we saw that they were eigenstates of the Hamiltonian and that did not change under the time evolution of the state. So to introduce interactions, what we need to do is to introduce nonlinear terms in the equation of motion, which will lead to coupling between different modes in the Fourier expansion of the fields. However, before we talk about the nonlinear terms that we can introduce in the Lagrangian or the Hamiltonian, let us talk about the vacuum in a interacting field theory. So in the non-interacting field theory, we denoted the vacuum state by a 0 inside a ket. So this is the So this was the vacuum in the free theory. So this vacuum is an eigenstate of the Hamiltonian with 0 energy and 0 particles. What we shall see is that for an interacting field theory, the vacuum, which is denoted by omega ket, now this also has energy 0, that if I have the interacting Hamiltonian H, the Hamiltonian of the interacting theory, that will give me 0. But it is not necessarily a state which has 0 particles. In fact, the vacuum in an interacting field theory is a much more complicated beast, which we shall explore in the lectures in the future. So the vacuum is one of the actors that enter in the story of the interacting field theory. Another important actor in that story are correlators. Correlators, also known as correlation functions, are generalizations of the Feynman propagator. So we saw that in a free theory, the Feynman propagator was defined by the vacuum expectation value of the time-ordered product of two of the field operator phi x and phi y. So this is an example of a two-point function or a two-point correlation function, also known as a correlator. In an interacting corner field theory, we shall see that all observables are built up from the vacuum expectation value of the time-ordered product of Heisenberg operators. And they need not be the same operator, they could be different operators. So the phi 1, phi 2, phi 3, these do not necessarily have to be the same operator. So you can say that the fundamental problem of quantum field theory is to be able to compute these endpoint correlation functions. These are called endpoint correlation functions or correlators. Of course, notice that these are numbers, these are functions, these are not operators. So these are all operators. Of course, the time-ordered product of operators is also an operator, but we are sandwiching it between the vacuum. So therefore, the vacuum, this is a expectation value or an average. Therefore, this is a function. So we could have written this as a function f of x1, x2 dot dot xn, which are the argument of the fields. So let's now come to the important question of examples of interacting quantum field theories. So what are some of the possible interaction terms, say for the quantum field theory that we wrote down, that is the free scalar field theory. So possible interacting, say, scalar field theories. So in the future, we shall see field theories which are not scalar, but for now, let us concentrate on scalar field theories. So a scalar field theory could be the free Klein-Gordon Lagrangian that we saw before. So this could be, for example, half of del mu minus half m squared del squared. And then we could add to it an interaction term, which I'm denoting by L int. And L int can have various forms. One could be that L int has the form of some constant lambda, a real constant lambda by factorial 4. The factorial 4 is a convention, phi to the power 4 of x. So if this is the interaction Lagrangian density, then the interaction Hamiltonian density would be the negative of this. So this would be lambda of factorial 4, phi to the power 4 of x. So such theories are known as phi to the power 4 theories. Another possible interaction term for this theory could be minus lambda by factorial of 3, phi to the cubed theory. And similarly, for this theory, the interaction Hamiltonian would be lambda by factorial of 3, phi cubed of x. So with the phi cubed theory, so a phi cubed theory would be much easier to handle than the phi 4 theory, but the phi cubed theory, if you look at the Hamiltonian, the classical Hamiltonian, you will see that it's not a bounded Hamiltonian. So if I were to work out the classical Hamiltonian, it'll have a potential energy term, which will be, if I plot it, so if I plot phi, if I plot the potential energy of the phi cubed Hamiltonian, then we will get something which is something like, depending on some parameters, it'll be something like this. And therefore, we see that over here, the phi cubed term, means that the Hamiltonian will not have a lower bound. So such theories will not be stable, will not have a lower bound to the energy, and therefore such theories are not going to be stable. Whereas, a theory like this is going to be stable as long as lambda is positive. And we can also, so this could be the plot of the phi cubed theory. So let me just, this is a phi cubed theory plot. Similarly, we could have plotted the potential of a phi to the power 4 theory. And the potential for psi phi to the power 4 theory, if phi is this, it could actually be of two forms. If the mass parameter m squared is positive and lambda is positive, we always assume lambda is positive, otherwise the Hamiltonian is not bounded from below. If this is the case, then the potential will have some parabolic form, some form like this. So near the origin, the potential where phi is small, the potential will have the form of half of m squared phi squared. But as we move away, the potential will have the form of phi to the power 4, because that term would be dominating. However, it is possible to write down quantum field theories where the mass term is not positive, but it's negative, or the mass squared term is negative. But as long as lambda is positive, such a quantum field theory also makes sense, but the form of the potential would be of a very different form. So it would have, when phi is small, of course, this is the term that will dominate. So because it is negative, it'll curve down like this when phi is small. But at some point, this term will start balancing this term. So it'll turn the other way, and then after a while, this will be the dominating term. So this will rise up. So as you can see that this potential and this potential has, they have very different qualitative features. For example, the lowest energy for this potential, there's only one point, whereas for this potential, there is some kind of a degeneracy in the lowest energy. Anyway, we shall return to these points later on in the course. So we have written two of these possible interaction terms. One thing to note is that if you are working in d equals to 4 dimensions, like the space-time dimension is 4, then it can be shown that, for this theory, lambda is dimensionless. And that also follows from the fact that phi, the dimension of phi, is 1. But here, if you're in d equals to 4 dimension, if this is in the phi cube theory in d equals to 4 dimension, the dimension of the field is still 1, but then the coupling constant is no longer dimensionless, and it has positive mass dimension 1. And this actually brings us to another important statement, which I will go into detail later, is that interaction Lagrangians, where the power of the polynomial in phi is greater than 4, in those Lagrangians, the coupling constant lambda will have negative mass dimensions. And this has consequence This has consequence that in the low energy limit of a quantum field theory, such higher order terms are going to be strongly suppressed. And we shall see that in some of the later lectures in this course. So this is the reason why we usually don't worry about interaction Lagrangians that's why we don't usually worry about quantum field theories, scalar quantum field theories in 4 dimensions whose interaction Lagrangians have power polynomials whose power is higher than 4. So we also talked about the complex scalar field before, and this is also a Klein-Gordon field. Sorry, this is KG. I choose to write it. And the interaction Lagrangian for the Klein-Gordon field has this form. For such a field theory, an interaction Lagrangian could be minus lambda by 2 phi dagger phi squared. For such a quantum field theory, lambda will also have the mass dimension 0. So what would be the form of the potential? The form of this potential, we have to draw a 3-dimensional picture. So since now the field is a complex scalar field, we have to draw it in a 2-dimensional plane. So this could be the real part of phi, and this could be the imaginary part of phi. And then if the mass term is positive and lambda is positive, then like before, we will get a potential which is of this form. So it looks like a ball. But if, for example, the mass term is negative, but lambda is still positive, then when the field phi is very small, the mass term will dominate, and therefore there we will have negative curvature. So it'll go down like this, and then at some point it'll rise up, and what we will have is something like this, where at the bottom we have this little dip. So this looks like the bottom of a wine glass or a Mexican hat. So such potentials are called Mexican hat potential, or also sometimes wine bottle potentials. So in this case, we see that when this is the case, the number of low energy states or lowest energy minima of the potential is given by a circle. So any point on the circle is going to be a point where the potential energy is minimum. So another comment I wanted to make about the interaction Lagrangian is that we always choose the interaction Lagrangian to be local. So for example, interaction Lagrangians, which involve, say, field at a point x and a field at another point y, we don't include interaction Lagrangians like this because this would be a non-local interaction term, and that would violate causality. And another thing is that although it's possible to write interaction Lagrangian, which contains derivative of the fields, the space-time derivative of the fields, we do not, for now, include such interaction Lagrangians.